This video is for homework 10 question 2. First one, wide sense stationary processes. A stochastic process is called wide sense stationary process if its mean is a constant and the autocorrelation is a function of time difference. WSS only uses mean and autocorrelation. In practice, they are much easier to get than second-order density. Based on mean and autocorrelation function, we can do many things already. We can do state estimation, parameter estimation, and prediction in mean square sense. In communication application, in most cases, we do not care too much on a specific value of a stochastic process. We pay our concentration on power of signal. The autocorrelation function RT1T2 for T1 equals T2 T1 is the average power of the signal at T1. We see that when the input is WSS process, the output of a stable LTI system is also WSS. Second one, independent increment process. It means xt1 minus xt2 and xt3 minus xt4 on non-overlapping intervals and are independent. So far, we see that Poisson process, random walk, and Wiener process are independent increment processes. It seems independent increment property is somehow related Markov process. Third one, a process xt is a Markov process if the past have no influence on the future when the present is known. We see that Poisson process, Poisson impulses, semi-random telegraph, random walk, and Wiener process are all Markov processes. In real world, many processes have Markov property. The binary transmission in early homework is a discrete time, discrete state Markov process. In that case, we call it Markov chain. Fourth, normal process. A process xt is said to be normal if the random variables xt1, xt2, xtn are jointly normal for any n, any t1, t2, and tn. The statistics of a normal process is completely determined in terms of its mean in eta t and autocorrelation RT1, T2. In general, eta t is a function of t. We classified Wiener process as one example of stochastic process, and we classified normal process as a property of stochastic processes. That is, we treat normal process as a larger class of stochastic process and treat Wiener process as a specific example. A process is said to be a strict sense stationary process if its statistics is not affected by a shift on the time axis. SS process requires fx of x1, x2, xn, and t1, t2, tn equals fx t1, x1, x2, xn, then t1 plus sigma, t2 plus sigma, and 2tn plus sigma. This condition is very hard to meet. 6.1 White noises. For Wiener process HWT, if we wish to discuss its derivative, Vt equals dWt over dt, we have E of Vt equals d E of Wt over dt equals 0, and Rv of T1, T2 equals alpha times delta of T1 minus T2. We know process Wt does have derivative. We use Vt equals dWt over dt just as a notation. When we need to do further discussions, instead of Vt dt, we use dWt. Wt is continuous with probability 1. It has differential dWt. Vt equals dWt over dt is a Gaussian white noise with zero mean and impulse autocorrelation function. We wish to determine more general white noise with zero mean and impulse autocorrelation function. A stochastic process Vt is said to be a white noise if E of Vt equals 0 and Rv of T1, T2 equals Qt1 delta T1 minus T2. The seventh one. A stochastic process xt is said to be mean ergodic process if limit when t goes to infinite of 1 over t2 from t to negative t of xt dt equals e of xt in mean square sense. In mean square sense is one kind of consistency. There are others in probability with probability 1 and so on. That's all.